In this lecture, we will learn about the understanding the designing concepts of orthopedic implants. So, ideally, orthopedic implants, once they are inserted into the body, we need to basically evaluate certain concerns. First thing is the biological environment should not get adversely affected by the implant material. So that is the first criteria, that if you are using an orthopedic implant into the body, it should not really adversely affect the implant material, though it will be affecting in a manner that it will try to assist the overall functionality of the system, but it should not adversely affect the overall harmony of this particular biological environment. At the same time, once the particular implant is being inserted into the body, the material itself should not degrade. It itself should not get affected by the surrounding host tissues and the fluids which are encompassing it. So the material has to satisfy two criteria: it should not affect the biological environment, and secondly, it should not get affected by the biological environment adversely. So both the conditions have to be satisfied by the orthopedic implant. And once we have learnt about the material and the overall biological environment, so then only it will give us a nice feeling about how we can utilize the particular material artificially and take over the functionality of the damaged or the unfunctional system. So understanding the correlation, what is happening between the structure and the properties of the natural tissue is very essential, because only once we understand what is the overall functionality or the properties of the natural tissue, then only we should be able to then only we will be able to replace them and assist them with replacing with certain synthetic or artificial material. So in continuity, the specific orthopedic need which is rendered by the tissue has to be replaced by a artificial implant, artificial orthopedic implant. So in totality, it becomes essential to see the correlation between what is the function of the tissue and how it is being affected by the structure. So overall structure of the tissue and its functionality has to be replaced exactly by the artificial orthopedic implant. So that gives the overall feel of this orthopedic implants. That first thing is it should not adversely affect the biological environment. Secondly, it itself should not get degraded or affected by the surrounding host tissues and fluids. So the calcified tissues which are present in the body, first of all, collagen is the protein component, and there are certain other organic phases, but one of the main components of this calcified tissues are collagen and inorganic compound, which is made up of hydroxyapatite. So organization of these two main components is essential for characterizing any bone structure, because only the way the hydroxyapatite and collagen, how they are twined, how they are coiled together to render the overall bone structure, that basically tells us that the organization of these two components is very critical in how the functionality is being rendered by the composition of these two, the protein and the apatite. So now it becomes essential to understand what is happening at the from the molecular level to the macro level, and how these entities are basically related or how they are being structured to give the final properties of the bone. So in the compact or cortical bone, there are 4 levels of hierarchy. The 4 levels which are starting from molecular to the macro scale. So at the molecular level, we can see that the collagen and hydroxyapatite, they form the basic molecular construct. So we have a collagen triple helical structure which is called tropocollagen, and then we have oxyhydroxyapatite, it is also called HAp, which form the basic molecular construct. Then we have intertwining of collagen and hydroxyapatite. So we get a second level of structure which is collagen and HAp, and this HAp is present both in the inter and the intra regions, fibril regions of the collagen, and later on it goes to forming certain fibrillar composites, fibers or fiber bundles, which show a kind of a lamellar type of a structure, and this lamellar type of structure eventually go on to forming certain secondary osteons or Haversian system, which gives the properties of overall bone tissue structure. So we can see there are 4 levels. Molecular level, we have collagen and hydroxyapatite, then we have organization of collagen and HAp, then it goes on to forming some fibrillar composites which form some sort of a lamella, and these lamellar units go into forming Haversian system. So we can see in totality this one represents the overall bone tissue, whereas the basic unit is construct of a certain molecules of hydroxyapatite and collagen. So we can see how this particular structure is evolving from molecular level when we have only hydroxyapatite and collagen, goes on to forming their organization in certain manner, goes on to forming certain fibers of fibrillar structure or lamellae type structure, and all these lamellae units go into forming osteons or the Haversian system, which is representative of the bone tissue structure. We can see at the third stage itself, we can somehow estimate the properties of this particular composite, because we are finding the arrangement of HAp and collagen as certain lamellae. So, we can go on to forming the local elastic properties of this particular structure, lamellar structure, but it gets even more complicated because the way the lamellar units are forming into Haversian systems, it becomes very complicated. But still it is again possible to evaluate the macro or the mechanical properties of this particular structure which represents the bone tissue. So, we can see the initially we generally can start with the overall apatite. So, we have a particular apatite formulation in certain regimes. So, we can see the apatite crystals which are somehow related, and then they basically, this collagen fiber and the structure of this apatite crystals, these are nothing but apatite crystals, and this is nothing but the collagen. So, a particular struct of it gives rise to, we have certain collagen molecules which are nothing but the formation of certain peptides and amino acids and proteins, and then we have overall lamellae kind of construct which basically evolves, and then we have apatite crystals which are embedded into this particular collagen. So, we have certain apatite goes on to forming certain apatite onto this particular amino acid acidic structure or the collagenous protein, and after that we get certain fibers which are nothing but the collagen fiber. So, we can see certain fibers which basically come out of it, and this particular fiber they start forming some concentric lamina. So, at molecular level we can see collagen plus some crystals of apatite which are nothing but the hexagonal type of structure. So, these are kind of nano crystals of hydroxyapatite, and then it forms certain arrangement to form some fibril kind of a structure, and then this is nothing but this is more of a micro level kind of structure, which is a construct which has been developed after the collagen and the HAp they have combined or intertwined. Finally, it goes on to forming osteons which are nothing but the arrangement of all these fibrils. So, they go on to forming fibrils out here, and eventually it forms Haversian canals. These are nothing but concentric lamina. So, concentric lamina go on to forming certain Haversian canal, and all these are basically present in the compact bone. So, we can see the overall bone structure is something like this, and we can see the compact bone, then it has all these systems which are composed of this Haversian canal system. So, we can see that generally the bone is composed mainly which has certain lamellae. In a 3D construct, we can see that all these laminas are somehow incorporated both as circular as well as all this kind of a cylindrical systems, which are nothing but, this is nothing but the lamella, and go on to forming the Haversian canals. The overall structure has already been defined in one of the earlier constructs. So, we can see that we have molecular structure which is composed of collagen and nano hydroxyapatite. A particular arrangement gives rise to the fibrils of apatite and collagen, and these go on to forming concentric lamina, and how this collagen and HAp basically can combine, I will show it little later. But once we have formed a concentric lamina, it goes on to form certain concentric lamina or a plane type lamina, which forms the osteons or the Haversian canals for this bone structure. So, we can see how the hierarchy is developing, starting from molecular level to the final macro level, which is nothing but the bone. So, hydroxyapatite is nothing but a hexagonal unit cell with a space group of P63 by M, and again it has a lattice parameter of A, small a, of 9.880 angstrom and C of 6.418 angstrom. So it contains two molecule units of CA5PO4 3 OH twice. So eventually it goes on to forming Ca10 PO4 6 OH twice. This is the formula for the hydroxyapatite, and since it contains two units of this smaller unit, it goes on to forming Ca10 PO4 whole 6 OH twice, and it is a small crystallite size, so it can get really embedded onto the collagen to form certain fibrillous structure. And again the X-ray diffraction of the bone, it shows considerable line broadening because it has a very limited crystallite presence. So it makes the identification of additional phases very difficult. With the presence of this nanocrystals, there is always some line broadening associated with the X-ray diffraction. But again because of presence of this calcium based ceramic, it has helped development of certain calcium based bioceramics, because the original or the biostructure of this particular bone is very similar to that of calcium based ceramics. So eventually we can go on to developing certain synthetic bioceramics which are based on calcium. So eventually what this calcium will do, it will assist the precipitation of apatite on its surface. So we have hydroxyapatite, synthetic hydroxyapatite, it will assist formation of osteoblast type cells onto its surface. So we can see hydroxyapatite, the overall crystal structure is hexagonal type P63 by M. It has a smaller lattice parameter of A 9.880 and C, the longer axis 6.418 angstrom. It contains two molecular units of CA5PO4 3 OH, and again because of the small crystallites, generally we observe a very broadening of the X-ray diffraction and very limited, this peak height is very small. So it makes the identification of certain other phases very difficult, and also it makes it difficult to understand how this hydroxyapatite is now bonded with the collagen, because it is very still, it is a matter of debate how this particular hydroxyapatite is now bonded with the collagen. But now the presence of calcium, this hydroxyapatite, it has now made development of certain bioceramics to replace the bone, to work as a bone implant very feasible. So we can see the structure of hydroxyapatite. It is again P63 by M. We can see all the calcium atoms just sitting as such. We have Ca10, so we have 10 molecules, 10 atoms of calcium, and Ca10 PO4 6. So we have 6 atoms of P which are sitting out as yellow atoms. Then we have oxygen which is again sitting at certain locations, and H. So H is basically present as OH twice. So we can see that there are certain units which are they are contributed only 1/4 in all the locations. So we have 1, 2. So basically there are OH twice is present. So we have Ca10 PO4 6 OH twice. So these are 1/8 which are being basically being included, 1/8, 1/8, 1/8, 1/8, and again 1/8, and again others are contributed by 1/4. So we can see there are this overall structure is now being present as a hydroxyapatite. Further, the presence of collagen triple helix can also be explained now, that we have amino acids which go on to forming polypeptides or proteins, and we have alpha chains which coil to form tropocollagen. So we can see in alpha helix. So we can see in alpha helix we have left-handed alpha helix. So it goes on to forming certain alpha helix, and we have all the peptides which are basically sitting here. So we have 3 units which basically go on to forming the overall length of repeating of length of 9.3 angstrom. The distance between two such basically peptides is around 3.1 angstrom. And again we can see that these go on to these basically they get untwisted to right-handed alpha helix structure, to right-handed helix structure. So this thing is now basically the basic chain. If you take, we have symmetry along the central axis, but now these basically this itself is now basically deformed to make it a right-handed helix. So opening of it basically now opens up this particular chain, and the distance between those two, it's around 2.86 angstrom, and the overall repeating part goes on to 10 such 10 such supercoils will make it 28.6 angstroms. So initially we had 3 units of 3.1 angstrom to make it 9.3, but in this case it basically opens up to reduce the distance between the vertical distance is reduced to 2.86 angstroms, whereas 10 units now go on to forming one repeating unit. So we have repeating from here to here comes to around 28.6 angstroms. And again the 3 of these particular helix structures, they go on to forming a coil, and then it forms a tropocollagen fiber. So we can see we have to start from the alpha helix structure, which is left-handed alpha helix with the the distance vertical distance of around 3.1 angstrom, and 3 units they form the pitch, which is nothing but 9.3 angstroms, whereas after uncoiling it, the twisted right-handed helix, it has now a distance, nearest neighbor distance of 2.86 angstrom, and the overall repeating pitch basically comes to 28.6 angstrom, and 3 of such structures they combine to form tropocollagen. And again, once the HAp and collagen are present, so the HAp-Collagen Organization that basically is controlled by some sort of a bonding at the molecular level, but still it is of under debate that how this particular bond hydroxyapatite is now being bonded with collagen to give out such a structure where hydroxyapatite is present both in the intra and the interfibril structures or zones. So we can see collagen and hydroxyapatite, there is some sort of arrangement which is now controlled by the bonding at the molecular level. It has also been observed in bone pathology that the collagen structure, it changes during its formation. So it can also result in certain inferior physical properties later on. So the particular structure is not really exactly consistent. Had it had certain sort of a controlled bonding with the HAp, it should be able to repeat itself no matter what, but that is not so. So there is something which is very tricky, which is happening at the molecular level, and that is dictating the overall bonding between hydroxyapatite and the collagen. And HAp is observed both in the intra as well as the interfibrillary region with the collagen. And again, their arrangement now basically can decide, or from that particular model we can basically decide how we can estimate the elastic properties which are now being weighed by their volume. So a certain volume of hydroxyapatite and certain volume of collagen can give us certain mechanical properties. So we can see that hydroxyapatite and collagen, they are bonded in certain manner. There is still there is not much of understanding of how this bonding is occurring, how this arrangement has been occurring between the two, and again the way the hydroxyapatite is now being present in the collagen, that can dictate the overall volume, and from the overall volume we can also find what is the elastic property which can arise out of this particular arrangement. So once this particular arrangement is formed, the lamellar type structure is formed. So that is formed by the fibrillar composites. So fibers, they go on to forming fiber and fiber bundles. So we had certain fibers which are basically being, and these fiber bundles, they go on to forming as certain lamellar type units. It can be circular lamelles, as we see there, that those are present in the Haversian system. So we have certain fibrous lamellar type of circular lamellar type units which basically form osteons or Haversian system. That happens in the mature human bone, whereas there can be also formation of straight lamellar units which form some sort of a plexiform bone, and which is predominant basically in the young quadruped animals like cats or bigger cats or rabbits type of animals. And now this particular structure is enough to predict the overall macro properties which are present for the bone. So initially in the previous case we had particular arrangement of bone and HAp. So from the volume percent we can estimate the overall mechanical properties, but once we have a lamellar type of a structure, in this lamellar type of structure we can identify what is the overall composition, but this particular system is very complex because of presence of certain porosity, the overall construct of this particular lamellae, how they are arranged, whether as a circular or as a planar or a plexiform type of a bone, presence of any veins which basically supply nutrients to the blood, any blood vessels to carry the oxygen, So this makes the bone very complicated, and this composite, the analysis of this particular composite to estimate its elastic property becomes much more complicated than the previous case. So we have a more of a Haversian type of a system, lamellar system, and that is now being formed from the construct of fibrillar composites which were earlier fibers. So these fibers go into forming lamellae, and these lamellae go into forming Haversian systems or osteons. So that is, now we can see there are 4 levels of hierarchy which is present in this particular construct of bone. But this multiscale hierarchy is very essential, because there are many properties which arise in bone. So we can see the stiffness part, and the stiffness arises from the composite structure, because we have collagen, we have macrocrystals of hydroxyapatite, and this collagen fiber, they go on to forming a certain construct, and that gives much more compliance or much more stiffness. This apatite or the crystallite regions, they can provide much more stiffness to the bone. We can obtain slower creep, because the slip at the cement lines which is present between the osteons. So between the osteons we have certain regime which is more like a cement type of a cement line type of structure. So slipping at those areas can give us slow creep. Again, cement lines, they also work as weak interfaces. So upon any impact, they can absorb the shock, they can absorb the energy to give out much more toughness. Presence of certain pores which are called lacunae, they also provide space for osteocytes or the living cells of the bone, and these osteocytes are essential for the survival of the bone. Again, bone cells at this level of scale, they basically permit remodeling, and remodeling is very necessary in order to undertake certain stresses. So bone cells at this level of scale, they allow remodeling the structure which is in response to the stresses borne by the bone. And again, these are the osteons or the Haversian canals. These are also called cylindrical pores. They contain blood vessels, and blood vessels are necessary for nourishing the tissues. And there are very fine channels which are called canaliculi, and they radiate from the lacunae. And again, it also assists in pumping the nutrients because of mechanical stresses, via some physical activity. We need to keep the bone nourishing, so we have to pump certain nutrients, and those nutrients are passed through this canaliculi or the fine channels. And again, the pore structure of the bone also helps maintaining the viability and adaptability to mechanical stresses. So we can see that each and every kind of feature or a structure has certain functionality. That stiffness arising from the composite structure, slower creep arising because of cement lines also assist toughening the material. Then we have ellipsoid pores. They allow the space for osteocytes or the living of the bone, and the bone cell, then they permit the remodeling. Again, we have Haversian canals or cylindrical pores which allow the carriage of the blood vessels, and blood vessels, they carry nutrients with themselves. Then we have fine channels, again they are required for pumping the nutrients, and the pore structure is very essential to adapt to the stresses and enhance the viability of the bone. So we can see the multiscale hierarchies arising from the basic construct of collagen and the apatite, and how these are going on, how they go on to construct various complex systems, whether it be lacunae, bone cells, Haversian canals or canaliculi. So basically all the arrangement of all this is very essential in terms of dictating the all multifunctionality of the bone. So it becomes essential to see what is happening in the bone, or what are the elastic properties of the bone. Though bone is basically viscoelastic, it has certain response with respect to time, but the elastic property itself can elicit in terms of understanding the performance of bone itself. So it becomes essential that we understand how the elastic properties are now being dictated. We can have quasi-static strain to understand stress strain curve, Young's modulus, Poisson's ratio, yield stress, fracture stress. So that will basically allow us to understand what is the response of a bone once a stress is being applied, what will be its stiffness, how much will it contract, what is the overall strength which it can bear, or at what stress it will basically fracture. We can also apply certain elastic plastic strain to understand the tension, compression, torsion, shear and fatigue behavior of the bone. And this is also essential because bone undergoes variety of stresses. while we are jogging we are undergoing impact, while we turn our foot we also undergo torsion. There can be again shear depending on how we are running, and all this compression is very essential because we keep jumping. If we are hanging from somewhere, bone undergoes tension. So the variety of stresses, those basically dominate the lifetime of the bone, and it becomes essential to understand them in entirety. So we can now model the bone and we can see how the stress response or how the remodeling of bone will occur when we supply it with a artificial implant material. So if you are inserting a artificial implant material into the body, so how the bone around it will reconstruct itself, that is also very essential in terms of dictating the functionality of the implant material. So it becomes essential to also identify what are the elastic constants of the bone, because it has been observed that there is a very strong relationship between the microstructure of the bone and its arising mechanical property. So that makes it very critical that we somehow basically be able to engineer the overall microstructure which is existent in the bone, and then identify its mechanical property, and then be able to design a artificial implant material which can mimic its microstructure and it also mimic its functionality in terms of mechanical property, in terms of its behavior, in terms of its corrosion resistance, in terms of its stress bearing or structural application. So bone is basically considered either transverse isotropic because of its hexagonal symmetry, and for that it requires 5 elastic compliance or stiffnesses to describe its elastic properties, or it also considered as orthotropic requiring 9 such constants. So basically now this helps understanding the overall resorption and the remodeling at the bone implant interface. So we can see if we are able to identify the overall elastic properties, we can understand how the bone resorption will occur or how the bone remodeling will occur at the bone implant interface. So first critical thing is the microstructure has certain dependence on the resulting mechanical properties, and bone we can consider either as transverse isotropic because of its hexagonal symmetry, or it is also considered orthotropic requiring then 9 components of elastic compliance or stiffness. So considering it to be transverse isotropic, we have the overall dependence of stress with strains sigma ij equal to the stiffness tensor which is of order 4. So in this particular case we have to define Ci_Jkl. This is nothing but the compliance matrix, and that will be resulting because of transverse isotropic. We can assume that properties along 1 2 and 1 2 and 2 1 they are nothing but the same. So the response at the other two region because of its hexagonal symmetry, we can assume it will be C11, C12, C13. So 1 and 2 it's same. So we also get then C13. So 1 and 2 basically are now being same. C13. And when we get C44, again C44 0. So that's how the dependence we can get, that we have these particular terms which basically are nothing but the same. So C23 and 13 they become the same. So the response of the stress in the third direction gives the same result either in 1 or 2. So we can see that particular part is arising out here. And when the bone is considered orthotropic, it means there is no dependence as such. So we require in totality we require 9 such compliance terms or the stiffness terms. So in this case we have Ci_Jkl, it becomes, there is no dependence, so it becomes C11, C12, C13, 0 0 0, and C12, C22. So there is, we can see there is no dependence between them. C23, 0 0 0, C13, C23, C33, 0 0 0. So we can see that dependence between them is now eliminated in this particular case. So again we can see there is no dependence out here, out here, and there is no dependence on the other side as well. So if we apply certain strain in one direction, it will also result certain, it will also have certain dependence, like it will also alter the strain, the compliance in the third direction. So stress in one, strain in 3 is basically affected, which is similar to strain in 2 and getting stress in 2 and strain in 3, but that is not arising when the system is orthotropic in nature. So we can see there can be certain dependence because of the transverse isotropic or because of its hexagonal symmetry. So we can see this side and this side basically is now symmetric, whereas it is not so in the third direction. But in this orthotropic case, we don't see any similarity either along 1 or 2. So again, the time since the bone is viscoelastic in nature, the viscoelastic properties of bone, there is no time temperature superposition to obtain its properties. So generally the time temperature superposition is done either by enhancing the temperature or by enhancing the time, we can get the similar performance, but that is not so in the case of bone. And again there are certain models which define the viscoelastic properties of bone. So there is one Kelvin-Voigt model which can portray creep very easily, or this Maxwell model which can render the stress relaxation part, and these both are only 2 element models. But because owing to the complexity, we require 3 element model or better for representing the actual system. So we can see that in the Kelvin-Voigt model and the Maxwell model, we only have 2 terms which are arising from the stiffness and the capacitance or the resistance and the capacitance type, which can portray creep, and Maxwell model it can represent stress relaxation, but we require 3 or a better model to represent the actual system of the bone. Just to give you a feel of the Kelvin-Voigt model, so in the Kelvin-Voigt model, we have the system where we have a resistance and we apply stress along this side. So we have it like this, and then so we have a capacitance, we have a resistance of K, capacitance of N, then we are applying stress in the other direction. So in this case we can see the sigma is arising, the stress is arising, it is now being shared between the component K and the component N, whereas the strain is similar in both the cases. So if you see overall response when sigma is constant, we will see that the strain gradually increases. So when sigma is equal to constant, with time the strain gradually increases, whereas once we keep the epsilon is equal to constant, we have more of a stress relaxation which is occurring. So when we have strain constant, we can see the stress relaxation which is happening out here. In case of a Maxwell model, we have structure which is more like this. We have the resistance and capacitance in series. In the previous case, Kelvin-Voigt model, we had this resistance and the capacitance in parallel, whereas in this case we have everything in series. So we have K and N. So in this case, if we apply stress which is equal to sigma K equal to sigma N, whereas the overall strain is now being shared between the two. So in this case, if we have a sigma constant, we can see the strain is linearly increasing, or again the stress part, it also is gradually decreasing. So we can see from the previous case, the Kelvin-Voigt model, it can portray the creep at constant stress, what is the overall strain which is happening, and the Maxwell model, how the stress is now relaxing itself. So we can see the stress relaxation part here and the creep part from here. When sigma is constant, how the strain is basically increasing. So we can see the creep part from here, whereas the stress relaxation part from here. But again, these are not sufficient to elicit what is happening at the bone level. So we require 3 elements or more to construct. So again we can have a construct of something like this. We can have the resistance and capacitance, and then resistance in parallel. So series of K1, K2 and N, and then we are applying stress, or it can also be, we can have this particular construct and then again resistance in series to apply the stress. So but again we need to have dependence which is more like e power I omega t, or sigma equal to sigma naught e power I omega t plus delta, where omega is the applied frequency and your delta is the phase lag which is occurring between the stress and the strain. So we can see this type of a structure is essential, or maybe a more complicated structure is more complicated arrangement is required to mimic the overall stress strain behavior of the bone. And going on to the biomaterials, we can see that biomaterials are, they can be basically classified into three broad categories of metals, ceramics and polymers. So in case of metals, these are nothing but the load bearing entities. So if you want entity to bear a load or act as a structural material, we need to incorporate metals, and we can see we have certain elements like 316L stainless steel, cobalt chromium alloys and titanium 6 aluminum 4 vanadium. And for any structure to bear the load, it needs to have very high strength as well as high impact resistance, and these metals are invariably used in the total hip arthroplasty. And it was, particular construct was developed by an English orthopedic surgeon, John Carnley, in 1982. What he has done is, he has taken the metal femoral processes and he has cemented it by polymethyl methacrylate with the acetabulum, which is now made up of ultra high molecular weight polyethylene, also cemented with the PMMA. So we can see that our femoral prosthesis and the acetabulum, they both are now being joined by PMMA, and the material is now being differed, like metal in conjunction with PMMA, which is now fixed by PMMA, and now it is fixed in the UHMWPE, which is ultra high molecular weight polyethylene, which is making the acetabulum. So we have the acetabular cup and we have the acetabulum and the hip and the femoral ball, which is now being sitting out here. So we can see that this metallic entity is now in contact with the ultra high molecular weight polyethylene. So now this particular construct, it has shown very dramatic improvement in terms of its longevity, but again there are certain concerns which are associated with metals, that though they are load bearing, they need not be corrosive or mutagenic or carcinogenic, because the basic problem with the metals is they tend to become highly corrosive once they come in contact with certain fluids, and they tend to release metallic ions which can become even carcinogen. So what has happened recently, that they are now being protected by certain ceramic layers. So they have certain porous outer coating, and this outer coatings are nothing but made up of certain ceramics such as hydroxyapatite, and then it allows the bone to grow onto itself and act as a biocompatible layer, and the pores basically assist them, the ingrowth of cells into the porosity and anchor them onto itself. So we can see basically metals are being utilized as a load bearing entity, whereas polymers, they are very good in they are very good, these are very nicely at the articulating surfaces, basically at the joint processes. It happens because they are highly compliant in nature, they can twist, they can basically change their shape once any force is acting on them. So they can accommodate release of the stress. They need to have very low coefficient of friction so that they can survive longevity, and they can ease out the friction which is happening between the adjoining articulating surfaces. They also need to have low wear rate in contact with the opposing surfaces. At the same time, they need to have very high strength as well as good corrosion resistance, but they tend to show very poor creep because they have very poor strength, they have lower melting points, so they show very poor creep resistance, and they show very lower resistance to the stress corrosion. So that is the basic problem with the polymers, but eventually ultra high molecular weight polyethylene has emerged as the ultimate choice. Also there are certain degradable polymers such as polylactic acid and polyglycolic acid, those are also have emerged as biodegradable polymers in case where we require a local or a very short term strengthening for certain things such as sutures. So we can, if we try to heal or particularly seal a particular location or a cut, and eventually that PLA or PGA dissolves with time, and it allows the new layer of skin to grow at that particular location. So we can see polymers for orthopedic applications, they are very good, basically serving at the articulating surfaces in the joint processes. They possess low coefficient of friction, they have lower wear rate, they require low wear rate in contact with the opposing surface, but the problem with them is they generally have poor creep resistance and poor stress corrosion resistance. But eventually ultra high molecular polyethylene has emerged as a ultimate choice for the acetabulum, and then it improves enhancing the life of the orthopedic implant. Additionally, certain ceramics and glasses also have come into picture, basically because of their two main features. First thing is, there are certain good mechanical properties and chemical properties. They have resistance to oxidation, they possess very high stiffness, they have low coefficient of friction, and they also have very good wear resistance. And also there is one limitation being imposed here is they require very small grain size, to the order of 4 to less than 4 micrometer, specifically for aluminum oxide with a certain purity. The additional advantage with ceramics is they can provide an interface of biological compatibility with osteoblasts. So this is the basic feature of this ceramic, which can provide much enhanced cytocompatibility with the real life tissues. So first of all, they have low resistance to oxidation, they have high resistance to oxidation, they possess very high stiffness, they have low friction and wear, and also they provide an interface which is very compatible to the osteoblast. So that makes it a very applicable material. So eventually there are certain materials which have been developed, certain ceramics and glasses such as bioglass, hydroxyapatite, which has emerged as a bioactive materials, and they allow the precipitation of apatite onto their surface, and then they can allow the natural bone to replace and take its place. Also there are certain bioinert materials such as aluminum oxide or zirconia, which can also allow the growth of cells onto their surface without any reactions. So we can see the on one hand, where we require metals for load bearing applications, polymers are good at the joint applications, whereas ceramics and glasses, they can serve as active agents in terms of assisting the cell growth and proliferation. So we can see there are three different combinations of metals, polymers and ceramics, which are essential in terms of undertaking three different functionalities. So ceramics and glasses, they are highly utilized for providing an interface with biological entities such as osteoblasts, and they can render their growth onto any surface, onto their surface, and they can also be applied as coatings onto the metals. So if I have a metallic implant and if we want to have interfacing with the real life cells and tissues, we can apply a porous coating of ceramics, so cells can really adhere themselves, they can interlock themselves with the pores, and they can start growing because of their good biological compatibility with the ceramics and glasses. So we can see there are certain traits or certain properties of this particular biomaterials, starting from the cortical bone. Depending on the type of strain which is being applied, we can get the elastic modulus between 7 to 30 or 40 gigapascal, and again it can be different in tension and in compression. So elastic modulus is out here, but the yield strength is approximately 114 megapascal. Ultimate strength, depending on whether it's in compression or tension, we can see that in compression the values are much higher than that of a tension. So we can see the tension values are 270 megapascal, where it goes to 400 megapascal under compression. Fatigue strength are to the order of 30 to 45, and also the densities are much more comparable to that of polymers. They are to the order of around 1 grams per cc, whereas polymers, they generally have densities less than 1 gram per cc or so. So we can see polymers, first candidates, they have again elastic modulus which are very low in comparison to that of a cortical bone. So we need to somehow utilize these polymers for some joint applications, but we need to somehow reinforce them with either metals or ceramics to improve their elastic modulus. Their yield strength also is very poor, compression ultimate strength is also very poor, but fatigue strength is approximately similar to that of cortical bone. Coming to the ceramics, they have very high elastic modulus. Once the elastic modulus is very high, they can impart stress shielding to the bone. So the bone will undergo modeling and will start resorbing. So that is not really good. Again, the ultimate strength is very high. It can go on to a couple of times, maybe 1 order magnitude higher than 1 or 2 magnitude higher than that of a cortical bone. So from 150 it can go to 3790, 3.7 gigapascals, which is very high. So that is not really good for replacing the bone. So we require it to again reinforce it with certain material or to induce much more porosity. If you are inducing porosity, then it can basically reduce the elastic modulus to a dramatically low extent, and that can now become comparable to that of a cortical bone. There are certain metals which also have been utilized very recently to serve as a bioimplant material. So stainless steel, cobalt chromium alloys and titanium 6Al 4V alloys. Again, their modulus is pretty high, elastic modulus going to approximately 200 gigapascal, whereas that of a cortical bone is around 15 to 40 gigapascals. Yield strength again it's very high, at 448 to 841 it can go up to 1000 for the commercial for the titanium 6 aluminum 4 vanadium alloys. The strength again it's to the similar order as that of a, it's much higher than that of a cortical bone, approximately twice, thrice that of a cortical bone. Again, the strength is pretty high, fatigue strength, because these are nothing but metals, so they tend to have very high fatigue strength. They can sustain very huge damages into them. Their hardness is again much higher than that of a polymer or of a cortical bone, but the elongation in fracture is again much lower than that of a polymer. And ceramics, they possess the least value of elongation because they are highly brittle in nature. So for metals, they have very high E, very high Young's modulus, but their elongation at fracture is lower than that of a polymer. Ceramics, they have very high modulus, elastic modulus is very high. The compression strength is also very good, but they lack in the elongation. The elongation is very poor. So elongation is to the order of elongation is very poor for the ceramics. And whereas metals, they perform very good because they can sustain very high damages. And the cortical bone, there are certain numbers which are not available right now. So but again, in terms of density, we can see ceramics, their density is to the order of 2 to 3 times that of a bone, whereas metals, they are pretty heavy. They go from 4.5 to around 7.8 grams per cc. So they are approximately a couple of times, 4 to 10 times much denser than cortical bone. So again, we need to introduce certain porosity into it, or provide certain structure which is much more compliant, and apply a certain coating around it, so it can really interface with the cells or the surrounding tissues. So we can see metals, they are highly tough, they have very high elastic modulus, which can lead to the stress shielding of the bone. So generally these metals are now coated with porous ceramics, and porous ceramic, they generally have densities to the order of 2 to 3 times than that of cortical bone. So porous ceramics can really serve as a similar material as that of a cortical bone. So you get toughening by metals, and we get compatibility by coating the ceramic onto this metal, and now it can represent a natural cell or a tissue, or similar to that of osteoblast, and then bone can start really growing onto it by anchoring and by finding the biocompatibility around it. Again, polymers also, they show very good promising, they are also promising candidate materials, and they are utilized basically in the regions where we have joints. So it can take care of much more compliance at the joints, and it can enhance the overall functionality or reduce the friction at those joints. So we can see this is the overall paradigm of different materials, starting from the natural cortical bone, polymers, ceramics and metals, and how they are basically linked to render a particular functionality. So in summary, orthopedic implants are the ones which do not introduce any sort of a adverse effect to the either to the biological environment, or at the same time don't get affected themselves once they are inserted into the biological environment. And there is some sort of interplay between hydroxyapatite and collagen, how they go into forming molecular chains, and how they go into forming fibrils, then onto lamellae, and then Haversian systems to form the overall hierarchical structure of the bone and get multifunctionality in the bone. So, the multiscale hierarchy starting from the cement lines or those canaliculi or those Haversian systems to supply the nutrients, at the same time remodel themselves when any stress is applied to them becomes very, very essential. So, multiscale hierarchy is one of the very critical components, and then it goes on to finding the viscoelasticity or elastic properties in the bone by applying Kelvin-Wurth model or Maxwell model or more than 2 or 3 element model in order to estimate what is the overall property which can arise from this particular structure. And also the overall bone structure is we need certain elastic constants to estimate the elastic properties. It can go on to basically understanding either taking them either as transverse isotropic or also taking them as to be orthotropic in nature in order to estimate the elastic properties. So, depending on that, we also will require certain stiffness or compliance values for perfectly estimating its response. And there are certain classes of materials starting from metals, polymers or glasses. It can even be composites, and we can also see there is a difference in terms of the functionality of starting from polymers, basically for serving as a compliant material, or metals serving as a structural material, or as a ceramic which is much more of a biocompatible material or interface which can interface with the biological cell to render the overall engineering of artificial implant material and make it serve as a replacement for the bone. So, basically I will end my lecture here. Thank you.